Yep. I'll just double check. We can go next.
Scroll using the mouse to change slides.
Yeah, you can do. I think just up and down, and then move your mouse however you like. We should be able to hear you once you're around. So you're here.
Okay.
Thank you.
Thank you.
All right, we're about to start. So Chris is just about to kick off in 3. We've got that live streaming as well.
Oh, there we are. Oh, yes. Okay, so I'm going to give a bit of a talk on the concept of quadrature, why we use it, why it's important. Maybe you already know what it's all about. Maybe you've got a different idea. Maybe you've got a mathematical definition. So first, we should start with a disambiguation. Which particular definition we'll be using? So in signal processing, quadrature phase is the two signals. So an oscillation where the two signals are separated by 90 degrees. Ignore most of the other stuff. So I'm not sure how many of you are familiar with the idea of a complex phasor or a phasor diagram. Any hands? All right, good, good. Bode plots? Good, good, okay. Well, I'll try not to dwell on either of these concepts too much, but a quick introduction. So there you have the magnitude plots for the cosine function, the sine function. These are actually in quadrature, which is lovely. So what's important about quadrature is that we can use simply the magnitude of both of these signals to reconstruct a phasor. So a phasor has magnitude or amplitude and phase. One of the problems with digitization is analog to digital converters only convert magnitude. So you lose, where's the phase information? So this is kind of quite important on the digitization aspect of software-defined radio, but I've got more of a hardware kink. So that's where I'll be approaching this discussion from. And also there's a parallel between the I and Q are used to represent the in-phase component and the in-quadrature component. Now, when you look at your software-defined radio, the variables get streamed, as your signal processing data stream, they come in through as complex numbers. So there's a real and imaginary component. They represent the I and Q components. Of course, there's basic truth there as well. So that, the bottom one is the phasor diagram. The last talk that I gave talked about the RF down conversion front end. So this is just sort of continuing on from that idea. So this is the RTL SDR chip that does the down conversion. And what you see on this side is the intermediate frequency signal out. Now that's one signal. You still need to be able to convert that to in-phase and quadrature components. Now, I did scratch my head a little bit about this because this is the digitization end, and they are using a single analog to digital converter. So, so perhaps they are deriving the quadrature components in the digital domain anyway. But there are a variety of different ways of doing this. There are some alternative chips that digitize only the in-phase and the quadrature components separately. So, like I said before, you can only, when you digitize an analog signal, you can only look at the magnitude, and you can do so at some single point in time. To derive any more information about that, you either got to have, to derive the phase relationship, you've got to have the quadrature signal, or you have to collect a large stream of signal magnitudes and then sort of derive some information about the waveform in itself and where that particular point in time sits with respect to the whole waveform. And so when you're in quadrature, I won't go into this, but it's also very mathematically elegant and convenient to modulate and demodulate in both hardware and software. The reason I sort of went down this little rabbit hole because I'm quite interested in using a spectrum analyzer as a front end. So you can pick up a spectrum analyzer off eBay for somewhere between probably about 800 to, I guess if you want tens of thousands of dollars. But this one set me back about 1,000. So I use that to just observe the spectrum. But it goes from this particular one is maybe 1 kilohertz or 100 hertz to 1.8 gigahertz. And what's interesting about them is they are effectively a complete radio receiver, like a very low noise, highly configurable radio receiver. The way they work is they actually continuously sweep the radio receiver through a very, very broad band range of signals, and then they only look at the magnitude, and that's how you end up with a sweep that represents the spectrum power. And yeah, if you're lucky enough to pick up one of those 80s relics, you may experience waves of nostalgia and the smell of cigarettes as it warms up. Which is the case for mine. So I don't know who used it before, but it came from Korea. So I've got a Tektronix 495P and a 492. These are just a few of the specifications. You'll see 100 hertz to 1.8 gigahertz, and then 50 kilohertz to 21 gigahertz. And these output the lowest intermediate frequency, which is 10 megahertz, which is pretty standard for these kinds of instruments. You can also get analyzers that will output the first intermediate frequency, which is typically around about 110 megahertz. So I'm interested in exploring the use of these particular ports on these instruments for sort of reconfigurable radio type stuff and digitized backends. Yeah, so basically what I want to do is take that single frequency, or that single signal, and convert it into I and Q components. So how do we do that? There are actually a large number of ways of doing this. Some of them depend on the sort of frequency range that you're operating in. Some of them depend on sort of like microwave, microstrip type arrangements, but because we're looking at to sort of about 100 megahertz, the techniques that are of the microwave domain, we're just not going to go there at all. So I'm going to go through delay lines, which are pretty obvious, polyphase filter banks, which took me a little while to wrap my conceptual head around, and establishing quadrature oscillators and down converting. Okay, so with a delay line, you can imagine that if you split a signal in half, you've got equal magnitudes, you send one signal down a physically longer path. You then end up with two sinusoids or two signal components that are actually out of phase by 90 degrees if you get the length of the cable correct. There are some issues with this. It's pretty basic. It's not going to work where you've got some deviation in phase and frequency. Like, this is just a really bad idea. Actually, no, sorry. Where you've got deviation in frequency, it's a bad idea because it's frequency dependent. So you've probably seen something like this before, maybe possibly in using dipoles to obtain circular polarization and stuff like this. They've got different length cables. And, anyway, it's not really that interesting, apart from perhaps in radar systems where they want to align the phase wavefronts. So you've got like switchable banks where you can actually change the physical length of the path so that the phase arrives at the correct sort of like angle. So this one's a bit interesting. Hands up, people who are into electronics. Yeah, okay. So when I first looked at this, I thought, geez, that's it's probably got a whole bunch of really wild mathematical derivation behind it. Yeah, I mean, it's basically, a lot of people, when they think of filters, they think, okay, well, first and foremost, it's the magnitude that I'm concerned about because you want to reject some kind of signal. This particular arrangement tries to exploit phase responsive filters as far as possible while leaving the magnitude the least affected. You obviously want to maintain a certain amount of signal strength. So I'll just flick backwards and forwards between a few slides here. So what you see here, a bunch of resistors and capacitors in the middle. These effectively form a series of low pass and high pass filters. You can think of them being cascaded or of sort of n order. There is a pretty hairy mathematical derivation for the system as a whole, if you go to that US patent. But yeah, so I tried to interpret it from more of an intuitive sense where I say, well, okay, I know pretty well how a Butterworth RC low pass filter works. It's pretty accessible to get a hold of, you know, the phase response as a function of frequency, magnitude response, and you know, that should look pretty familiar to most of you. So what you'll notice is, though, that on the low pass, you have a phase shift of -45 degrees at the corner frequency. So I'm going to jump out here because the mouse isn't very good at this, but this line here, the corner frequency, you see the phase shift is -45 degrees. So that's interesting because in Quadrature, of course, you want 90 degrees. So what we can actually do is use a low pass filter and a high pass filter because they create opposite phase responses, and then you can actually use the difference of the two. So you've got -45 on the low pass, you've got +45 on the high pass. Keep in mind at this particular frequency. So you've got 90 degrees, you've got Quadrature at that particular frequency. The problem is that's also the -3 dB point, so you've got loss. What's arguably even more irritating is that you have a pretty strong roll-off regardless of where you sit, because you've got a high-pass filter and you've got a low-pass filter. So now if your frequency deviates either side of that center frequency or that corner frequency, you're going to have a pretty substantial amplitude modulation to go with your frequency modulation. And BYO algebra, because there's no way I'm going to put all this up here, but the relationship for the phase shift is equal to the arctan of 1/2 pi FRC, which is pretty simple. So that's for a single pole. So going back to here, we can cascade these, right? So in that particular instance, you've got +45 degrees from one filter and you've got -45 degrees for another. What if you cascade them? Then you might want, in the last case, I've got 4, and each filter contributes 12.5 degrees. The great thing about doing this is that you end up moving your operational point more into the pass band of the filter, so you're not attenuating the magnitude quite as much. Okay. So I went to LT-Spice. This is the top chain is 4 low-pass filters. Each one is buffered using an emitter follower. That's kind of important because the filters will load each other. So there are some challenges there when it comes to making longer chains of filters. So yeah, each one imparts a plus or minus 12.5 degree shift at that particular center frequency or that corner frequency. These are the Bode plots. So sorry, this is really difficult to see, but so the green is the in phase. The solid line, which is this one here that tails off in magnitude, I believe that's the low pass. And you see the dashed line in green is the phase response. Then the blue is the high pass, and that's the magnitude. This is due to transistor parasitics here. So you kind of just try to ignore what's happening higher than about 100 megahertz. It's really difficult for these particular transistors to operate in this region. So I designed it with a sort of frequency of operation of around about 10 megahertz, which is this center point here. And you'll see at 10 megahertz, the red line is actually the difference in phase between the two filters. And you'll see there's a pretty decent, if you can see what I'm seeing, which is tough. This is 80 degrees and this is 120 degrees. So we sit fairly square in the 90 degree sort of design set point. But you still see that there is a phase shift either side of that 10 megahertz, which is, it's better than the first two things we looked at, but in my opinion, it's still not good enough. because I would like to be able to use this for both 10 megahertz and 10.7 megahertz. So, 10.7 megahertz is a fairly common intermediate frequency. I'd like to be able to use this on a few different systems. So, okay, despite all that hard work, not really the best. But actually I came across this, and it should have twigged a lot sooner when I was staring at a few of the digitized radio systems, because this is how they pretty much all do it. So you can generate quadrature in the clocks rather than having to modify the signal directly. You modify the clock that you use to down convert in the super heterodyne architecture. And you can do that actually really conveniently using very high speed logic, which is convenient again, because we all know that, well, not all of us, but most of us know that RF electronics can be a little bit picky at the best of times. So look, if you can work in the digital domain, it's all sort of fairly simplified, provided you implement it correctly. So what you see, this image over here, if you're not close enough, is you have a square wave typically that goes into the system. You invert the square wave, and the toggle of the D flip-flops or the D latches are triggered by the rising edge. So if you've got an inverter, then you're actually effectively toggling the top flip-flop on the rising edge and the bottom flip-flop on the falling edge. And then you generate waveforms that look like this. So this is your clock, and these are the outputs of your D flip-flops, which are non-increased. So there's a quadrature signal. Now they're square waves. This is really, really interesting when it comes to mixers, but I have a feeling this is a talk for another day. And I'd like to be able to do that when I've actually built it. So it's probably going to be a lot more fun. So there are some other issues with this. Of course, it's a bit simplified when you use logic, but that makes it very convenient when you're driving mixers, diode mixers. But it can also introduce phase noise in the form of clock jitter. So you have some sort of very short-term deviation in the clock, and that could introduce phase noise in your final down-converted signal. And this here is sort of hypothetical or the theoretical architecture of a system that takes the intermediate frequency in. Now this would have to be a lot higher because this down or up converts, so you can't convert to the same frequency. If you're going to take 10 megahertz and you're going to generate signals at 10 megahertz, well, you need to convert to a different frequency first and then return back down to it. So there's all sorts of design decisions that go on there about choosing frequencies with relation to filters that are already available and all this kind of stuff. But as far as the theoretical model is concerned, your 10 megahertz or maybe your 20 megahertz signal, if you've converted up to 20, comes in here, you put in your in phase and your quadrature signals. As part of that down conversion process, you impart that quadrature upon your RF signal. And then you low pass filter it because you have harmonics from the square waves that you've just mixed with. And then you can digitize the I and the Q in phase and quadrature. Yeah, so basically the whole idea of this is I wanted to actually be able to show you like a hardware prototype because I've got all the bits. I've just had my, my time split between a few different things. So I'll actually be implementing the polyphase filter and the local oscillator methods. Then I'm going to try and characterize probably a lot of calibration work with the polyphase filter, but there's probably also a bit of work in trying to characterize the phase noise from the clock jitter in the local oscillator method, and I'll probably produce a PCB. So I know there are some people that are kind of interested in mucking around with this stuff, and let me know if you're interested. But yeah, probably if I do a next talk, it would be on the digital logic and how you can utilize digital logic in high-speed RF. Yeah, so that's it.
Any questions?
Yeah.
How does the RTL do it?
Yeah, so I've got the slide. It was a little bit difficult to obtain the data sheet because I did look for this particular RTL integrated circuit. It's Realtek. But they appear to have done like an entire in-house development type thing and not made the details publicly available. So this is the only image that I managed to get of it. And I'm not sure if this is the work of some reverse engineering, but this is kind of interesting. I did sort of scratch my head over this for a while because they have the ADC block at the beginning. So, but at the same time, there are other digitizing systems that that actually produce the digital clock-based quadrature and then mix one RF signal or the intermediate frequency down into in-phase and quadrature using the clock rather than some other means. So that's about as much information as I could find. There's a one-page sort of text description of what this chip does. But as far as the internet community is concerned, there's a bit of hocus pocus, and they'd rather not have you understand it, I believe. Yeah. Yeah. Yeah.
Take filter requests.
Filter requests?
1.6 meter.
Yeah, that's another project that I'd love to work on.
Great.
Yeah.